We're now going to look at sampling distributions with two samples, both averages and proportions. In this case, we're a long way from the central limit theorem and the actual intuition about what happens there from the approximation from a binomial or its big brother, the multinomial, to the normal. In this case, these cases, all we're really concerned with is how to calculate probabilities and understanding the differences in the formulas for all these different cases. With the one sample cases that we've looked at, first with the average, we had a z equal to x bar, the limit, minus the mean mu, divided by standard deviation sigma sub x bar, and then we had a formula for sigma sub x bar. Alright, sigma sub x bar was sigma divided by the square root of n. And for proportion, the z was the limit, which was p hat, right, sample proportion, minus the mean, true population proportion, divided by the standard deviation of the distribution sigma sub p hat, where the standard deviation sigma sub p hat, square root of p 1 minus p on n. Okay, but in either case, the z is always a limit minus the mean of the whatever distribution, normal distribution, divided by the standard deviation of the particular normal distribution. Okay, and in each case, the z will have that form, and the standard deviation will be different depending on the circumstance. Alright, so we're going to start with two sample averages. What we'll have is two groups, two samples. You could think of them sometimes as subgroups of the one population, males, females, for instance, Republican, Democrat, whatever. But essentially two different groups with their own population parameters, the averages, standard deviations. Okay, so let's call them group 1, group 2. For each group there will be a population mean, mu1, mu2, and a population standard deviation, sigma 1, sigma 2. When we look at samples, our notation will be similar. We'll have just put subscripts. We'll have a sample size n1, alright, and a sample average x bar 1. N2 for group 2 and x bar 2 for group 2. Okay, so now we have the same bits of information about the population and the sample, but now we have two groups. And in the long run, when it comes to 215, we'd like to know if these two groups have the same population means, or if the population mean of one is bigger or smaller than the other. Okay. The formulas in this case, the z will be the sample difference, which will be a limit in terms of the sample, minus the difference in the population, divided by the standard deviation of the particular distribution, and the distribution is the distribution of sample differences, x bar 1 minus x bar 2. Alright, so it's a distribution of x bar 1 minus x bar 2, so we have a limit in terms of x bar 1 minus x bar 2. The true value will be mu 1 minus mu 2. Okay, and this will be approximately normal under certain circumstances. The standard deviation sigma sub x bar 1 minus x bar 2. Alright, remember this x bar 1 minus x bar 2 is a subscript, is the square root of sigma 1 squared on n1 plus sigma 2 squared on n2. Okay, and even though these formulas start to get a little heavy and cumbersome, the process of all of this is the same. We need certain information to get a mean and standard deviation of a normal distribution. We need a limit of a normal distribution, direction, which way we're going to go, and then we find the probabilities, when we translate to a z distribution. Let's look at a problem involving sampling distribution probabilities with two sample averages. Alright, the last one there on this page. Recently, and this starts off like a previous problem, but now we have two samples. Recently, the fruit and veggie section of a supermarket has been remodeled. Before the remodeling, the average expenditure of 100 randomly selected customers was $16, while after the remodeling, the average expenditure of 100 randomly selected customers is $18. Okay, looks like the average went up, right? Assuming that the standard deviation has remained unchanged at 9, so before and after the change of before and after the remodeling it was $9 for the standard deviation, and assuming that the true average expenditure has not changed, right? mu1 minus mu2 is 0. What is the probability of getting a sample increase as large or larger than what we see here? Okay. So, population information. We have two groups. Before, which we call 1, after, called 2. Alright, in both cases we have a sample size of 100 randomly selected customers. Before the remodeling, right, the average expenditure was $16. And after remodeling, the average expenditure was $18. Sorry, I call that population. That's not true, clearly, right? That's basic sample data. Alright, when we want to calculate our probabilities, we need the population data. Alright, what we need is mu1 minus mu2. We need sigma 1 and we need sigma 2. Alright, here it says assuming it is the standard deviation has remained unchanged at $9, means that before and after remodeling, the standard deviation of expenditure was $9. And assuming that the average expenditure, true average expenditure, has not changed. Who knows what it is? Said it was $15 before and after. Said it was $15.25 before and after. But whatever, they're the same. So mu1 minus mu2 is 0. Okay, so we have that, and then the next last thing we need is the limit. But the limit from this case is from the sample. It's not always the case. Sometimes you're not given sample data like in this question. So the limit x bar 1 minus x bar 2, 16 minus 18 is minus 2. Okay. So the question is, what's the probability of getting a sample increase this large or larger? Right? And this minus 2, which is going to disturb a few people, is the sample increase. Remember, it went from $16 before to $18, so the negative 2 is an increase. If the increase is going to be larger, say from 16 to 19, it will be negative 3. So what we're talking about is the distribution of sample differences, x bar 1 minus x bar 2. The mean of that distribution is mu1 minus mu2 is 0, we have a sample increase of $2, which is on the negative side, and increases larger or larger, right? Remember, now -3 would be down here, which would be a larger increase, and -4, etc. And so this is the probability that we're looking for. Okay, so we're going to translate that to a z, but we can draw our distribution or not. It doesn't matter at this point. Hopefully you don't need to draw your normal distribution. Okay, the probability that we're looking for is that the probability of x bar 1 minus x bar 2 being less than -2, where the mean of this normal distribution is 0, and the standard deviation sigma sub x bar 1 minus x bar 2 we have yet to calculate. Alright, so let's do that calculation now. So sigma sub x bar 1 minus x bar 2 is the square root of sigma 1 squared on n1 plus sigma 2 squared on n2. Square root of the whole thing. Alright, sigma 1 is $9, square that, divide by a sample size of 100, and sigma 2 is the same thing. It's not always the same. In this case, we're using them both the same. So let's go to Excel, do that calculation. It's the square root of 9 squared divided by 100, and then, oops, sorry, I didn't square it. 9 squared divided by 100 plus, and the same thing, 9 squared divided by 100. Alright, the answer to that to 4 significant places is 1.273. Alright, so now we have a normal distribution in terms of sample differences. And next calculation would be the z value, the limit x bar 1 minus x bar 2 minus the mean of the normal distribution of the sample differences, mu1 minus mu2 divided by the standard deviation of the sample differences. Alright, the limit x bar 1 minus x bar 2, alright, it's the -2 from up here, or the -2 from our diagram, it's a limit, minus the mean 0, divided by the standard deviation of 1.273. Let's go to Excel quickly to figure that out. So that's going to be equals -2 divided by the standard deviation to 2 decimal places on the z, that's -1.57. Okay, and so what we're looking for on the z distribution is the probability of getting less than 1.57. It's an area in the lower tail as in the above diagram, so it's a half minus the value from the table from -1.57 to 0. Let's find by normal distribution tables. Alright, 1.57. Okay, we'll be here. It's 0.4418. And the answers to that will be 0.582. Okay, so the probability of getting a sample increase of $2 or more, if there is no real change and the standard deviations didn't change, is just over 5%. And so it's sort of unlikely, but not that unlikely. Okay, so it may have been no change there, but we're just looking for the probability.